My name is Brian, and on behalf of my co-author and advisor, Nikiforakis, today I'll be presenting our work on web application fingerprinting and how we went about trying to improve it in some nice ways. So I'm sure it's not a surprise to anyone in this room that open source web applications are the heart of the internet today. Applications like WordPress, Drupal, and Joomla alone make up roughly 40% of all websites online. And some of these sites are very important, like whitehouse.gov is powered by WordPress. The Canadian government's website on safety alerts and advisories is run by Drupal. And many businesses, such as hotels, use Joomla for check-in and check-out services. If you're interested, I checked the downtown Philadelphia website does not use Joomla, though. So it's no surprise that the high adoption rate of open source web applications, along with vulnerabilities being logged publicly in CVE databases, magnifies the effects of any vulnerability of these applications. And this means that effective web application fingerprinting is a very powerful tool, since if you know that a particular version of, say, WordPress is vulnerable to some exploit that is publicly available, all you have to do is identify the, say, millions of sites that are using that version to have tons of targets if you're an attacker. So how do we fingerprint web applications? Well, there's two main ways, and they both look at different bits of content that web applications produce. So the first is dynamic content fingerprinting, and this generally is comprised of HTML content. So the reason why we say dynamic is because the HTML of a page will be dynamic based on the user a lot of the time. So like if you're signed into, say, a WordPress site, your username will be in the page, so it's going to change from user to user. But there are bits of text within this content that can be pulled out using regular expressions. So like here in this example, WordPress 5.8, by default will add this meta HTML tag that just tells you it's WordPress 5.8. And there's also cases like, for instance, at the bottom of a lot of WordPress sites, it will say powered by WordPress. So if you're a fingerprinting tool, you just got to look for these strings and you trivially know that this is WordPress 5.8. This can be removed from sites, obviously. So when dynamic content fingerprinting doesn't work, static content fingerprinting comes into play. And so what static content fingerprinting is looking at static content that doesn't change from user to user, like JavaScript files, CSS files. These will change typically from version to version. So what we could see here is in WordPress version 5.8, this particular JavaScript file had a post per page attribute of 40, and in the next version, 5.8.1, it changed to 80. That was the only change within this JavaScript file. And as we all know how hashing algorithms work, that one change makes all the difference and completely changes the hash value. So if you're a fingerprint tool and you want to be able to identify what version of WordPress is running on a site, you could go through the source code of all WordPress versions offline in a training phase and calculate the hash of all these static files and store them in a database. Then you could go online, grab the same file from a site, and if you see that, say, the hash of this JavaScript file matches the first one, then you could confidently say that this is probably WordPress 5.8. And as you add more files, say you do this for 10 different files on a site, you could grow your confidence. So in this work, we wanted to answer a few research questions. The first is, how effective are modern web application fingerprinting techniques? On top of this, we want to know how robust are these techniques to the noise that's added by real-world sites. So we wanted to test the performance both in a best case scenario, so when you install a web application right out of the box and make no changes, and then compare that to real-world deployments of the same web applications. And then lastly, we wanted to know what factors influence the performance of these techniques in the wild, and can we address them and remediate them in some way? So to answer these three questions, we created WASABO, which is a general web application playground sandbox system. So there's multiple parts of this, so I'm going to start kind of on the left here. If you wanted to, say, install your own WordPress site, it's very easy. You just download the source code, throw it into an Apache web server, run through all the GUI forms that are in your browser to set up things like where your SQL server is, etc. This is not something that will scale very well for all versions of WordPress. If you wanted to automate this process and test against every single version of WordPress that was ever released, which is in the hundreds of versions, you can't just manually do this for everyone. So we wanted to use Docker to come up with a way to combine different versions of PHP and MySQL, which are the two main requirements for any open source PHP web application, along with installation scripts to encode the way to set up these sites. So essentially, we created manually a configuration for every version of these web applications. And on demand now, if you play with our tool, you can set up any version of any of these web applications, and it will grab the right version of PHP, the right version of MySQL, and it will send the right post request to the server to install everything. Then what we can do is, on the right side of this figure, we can run some arbitrary code. So in our case, we're running fingerprinting tools, which are also Docker containers, and recording what the output of them is. We could also do this for sites on the internet. And we could pipe all of our network traffic through a network middleware module, which I'll talk more about in a bit, but essentially allows us to make some changes to the content on the fly to help with fingerprinting. So to find the fingerprinting tools we wanted to test, we essentially just conducted a thorough literature review, looking for commercial and academic open source fingerprinting tools. And the open source bit is important because we wanted to know what's going on under the hood with these tools. So we found a good mix of tools that use dynamic and static fingerprinting, and also those that have a varying number of requests towards the site that they're trying to fingerprint. So the first thing we did is we looked in our best case scenario, which of these tools, or what's the performance of these tools in just identifying the type of web application. We're not even worried about the version. We just want to know if this is a WordPress site, can you tell me this is a WordPress site? And what we found is, so the two tools on the left here, so Blind Elephant and Version Infer, they both use static content fingerprinting. The two on the right, they use dynamic content fingerprinting. And the main takeaway here is that dynamic content fingerprinting in general is just better in a best case scenario, since these sites will just tell you what they are. So if you're able to just pull that information out, there's really not much you have to do. You're only going to run into trouble if you try to be fancy and use static content fingerprinting. So we wanted to also, like I said, take this to the real world and see how do these tools fare against real sites that have been worn down by use and modified in many different ways. So this is not a trivial process to find sites that are online using the right kinds of web applications we're interested in, because these sites will obviously not want to tell you this. It's bad OPSEC to just advertise this stuff. So what we found is that we can use the showcase pages of each web application to find sites that are using that particular web application. So for instance, WordPress will have a page that tells you, here's all the brands that use WordPress, just as an advertisement for you to go and use it for your own website. So in total, we found 726 websites that through this methodology. So we determined a baseline performance against all these sites, just right out of the box, just throw our fingerprinting tools at them. And then we also repeated the scans with a series of network transformations applied to the network traffic coming back to each tool from the sites. So we created 3 different network transformations, very simple things to get around a few of the most common bits of trouble that fingerprinting tools run into. So first, we add a cache breaker to all GET requests made by these tools. And the idea here is that we found a lot of CDNs will cache static content and minify JavaScript files and CSS and files like that. And while that does improve the performance of the sites, which is why they do it, it breaks static content fingerprinting because removing the new lines and spaces and stuff changes the hash, obviously. We also try to replay all requests from the fingerprinting tools with a real Chrome browser to get around bot detection. And lastly, we have a very simple path prediction algorithm, which we use to identify cases where a web application is installed in a directory that's not the root of a web server. So for instance, again, using WordPress as an example, if, say, the WordPress site is installed in the /wp/ directory of the web server instead of just /, all of the requests will be wrong if you're looking for things in the root. So we just grab the homepage of the site. We look to see, is there a large percentage of the resources that have the same parent directory? And we just redirect our requests to that parent directory. So I'm sorry about all the numbers. It's not very pretty to look at. But essentially what you want to look at here is the two columns, the third and fourth column from the left. The third column is our accuracy in the lab, and the one on the right is the accuracy against the real site. So we see a large drop-off from our best case scenario to the real world scenarios. And this makes sense because of all the reasons that I just mentioned. There's all these little peculiarities of different sites that break fingerprinting. However, the good news is that using WASABO and using these network transformations, if you look at the column titled Combined, we're able to improve the performance of these tools pretty dramatically. In the best case scenario, we have about 23% more correct identifications just by using WASABO. And really the important point here is that it's trivial to set up your fingerprinting tool to use WASABO. It's essentially just proxying your traffic through it, and you automatically just get this free performance improvements. There's no change to code, and it works with any fingerprinting tool because it's completely agnostic to the functionality of the tool itself. So the takeaways here are that fingerprinting tools perform well in a best case scenario in the lab with newly installed web applications with no anti-fingerprinting techniques applied, no changes, they do generally well. However, these tools rely often on web applications remaining completely unchanged from training. And by training, I mean either from a developer manually creating regular expressions to pull out version strings, or from the time when these hash databases are computed. So WASABO can be used to improve the performance of, like I said, any tool with very minimal setup, but it's still not the end-all be-all. There still is a really great need for new tools and techniques that are more resilient to these kinds of things that break the current fingerprinting tools. And if we're able to get to that point, we can secure online infrastructure by finding vulnerable hosts in networks, and also study internet-wide trends by determining what sites are using which versions of web applications. So there's a lot that I didn't get a chance to talk about here just due to time constraints, but I highly recommend visiting this link here. You could play around with WASABO and definitely check out the paper. We have a lot more in there, a lot of really cool case studies and stuff. So thank you for your time, and I'd be happy to take any questions.